So far, we've looked at and you've built some circuits that might look like the series circuit shown below. We've imagined that the electrons come out of one terminal of the battery and flow through the wire and go back into the battery, as though the electrons themselves are making continuous laps around the circuit. In a battery-powered circuit, this is true. The current always flows in one direction. This is called direct current, typically referred to as DC. But current doesn't have to keep flowing in one direction. When electrons flow through the wire in a light bulb and cause it to light up, the light bulb doesn't actually care whether the electrons are flowing left to right or right to left. If you remember when you built your circuits to try out some different kinds of series and parallel circuits, it didn't matter which direction your light bulb was facing. If there are electrons trying to squeeze through that filament, that little tiny wire inside the light bulb will glow and the light will light. And it doesn't matter whether those electrons are trying to squeeze through in one direction or the other. If we could take the same single group of electrons and push them back and forth through the light bulb over and over again, the light would indeed stay lit. Whether electrons are flowing this way, to the right as shown in this picture, or this way, to the left, the light bulb will light. And particularly if the electrons keep switching directions, the light bulb will in fact stay lit. When you reach the slide, please pause for a moment and go to the second link that's shown in this Moodle module. I've included a copy of the website below. This shows you an animation that shows when the direction of the current alternates or moves back and forth, we're generating alternating current. After you've had a chance to look at this animation, come back in and continue this presentation. You can make a comparison between alternating current and the waves. In this case, the black line that's going up and down shows the voltage at any given time. So you'll see that the voltage goes from 0 and it rises very high, and then it drops and it actually goes negative. That means the electrons have turned around and are moving the other direction. And then the voltage goes up high again and then back low. So the voltage is continually switching directions, and it's going from a peak of 120 down to a trough of a peak of 170 down to a trough of negative 170. That's pressure being applied in one direction and then in the other direction. At this point, you'll need to get out your notebook and take some notes on the difference between alternating and direct current. In alternating current, or AC, the electrons move back and forth. The direction changes many times every second. Here in the US, the direction changes 60 times every second, or 60 hertz. You may have seen this 60 Hz as you tried to find information on appliances at home. This is different in other countries, which is why you can't simply plug your hairdryer into a plug in France and expect it to work just right. For alternating current, the voltage goes way up and then way down. The voltage is continually changing. So the effective voltage coming out of a plug in the wall, for example, is 120, but at any given instant the voltage may be higher or lower. The 120 volts is actually an average. Wall outlets, when you plug things in your house, are alternating current. One of the good things about alternating current is that it can be sent long distances. So we can generate alternating current at a power plant and send it through transmission wires many miles to your home. Direct current, on the other hand, the electrons always move in one direction, and the voltage is constant. A small battery, for example, produces a voltage of 1.5 volts, and that voltage is constant. It doesn't change. It doesn't go up and down. It just stays at a constant 1.5 volts. Batteries produce direct current. One of the downsides of direct current is that it's difficult to send it over long distances. You can imagine that you don't often see a battery with exceptionally long, mile-long wires connected to it, because direct current tends to lose its power as you send it over long distances. So how do we generate alternating current? Well, the picture below is intended to represent a small slice of a wire. We're going to take those electrons and imagining imagine that you're pulling those electrons back and forth with a magnet. So if I were to place a magnet on one end of this wire, the electrons, which are negatively charged, might move towards it. If I then were to take the magnet and switch it around, place it at the other end of the wire, the electrons would move back. So if we could move this magnet back and forth to one side to the other side, to one side to the other side very quickly, then we could get those electrons to move back and forth in the wire quickly. How on earth is this useful? Well, the way generators work is instead of taking a magnet and moving it back and forth across a wire, we actually hold two magnets in place and spin a wire in between them. And effectively, this ends up having the electrons pushed back and forth. If you take a minute again to go back to the link that I asked you to look at previously, you'll see that there's a wire spinning in between two magnets, and it'll show you that the voltage in that wire is going up and then going down, and going up and then going down. So the electrons move back and forth because the wire is continually spun near a magnet. The next thing we need to learn about is transformers. And again, this is a FYN or a for your notebook. Transformers change the voltage of electricity flowing through a wire. You can have a step-up transformer that takes low voltage and makes it very high, or you can have a step-down transformer that takes high voltage and makes it very low. Why do you need to change the voltage? Well, the electricity that's being sent through high-tension wires and even through the wires attached to telephone poles that go down your street is at a higher voltage. It's being sent under higher pressure because it's more efficient to send it under higher pressure. But you don't want that electricity under very high pressure coming into your house. If you plugged your hairdryer into an outlet that was much too high of a voltage, your hairdryer would blow up. The pressure of the electrons would blow up your appliances. And so one of the things that we need is a transformer. If you look on many telephone poles, you'll see something that looks like a light gray garbage can mounted up towards the top of the telephone pole. That's actually a transformer. And you'll notice that there's a transformer anywhere that there's a line that goes from the telephone poles into your house. That transformer is stepping down the voltage before sending it into your house. Once the electricity gets into your house, it can operate at two different voltages. Most things in your house are 120 volts alternating current, where the current alternates 60 times per second, or 60 hertz. The regular outlets that you plug most appliances into are the 120 volt outlets. For appliances that require higher pressure, your house also has two 40 volt lines. These are things like your clothes dryers, if you have an electric oven, or a refrigerator may plug into one of these depending on its size. These are things that need a lot more electricity. And the plugs are shaped differently, so you can't accidentally plug your toaster in where your clothes dryer belongs. With such high voltages flowing through your house, we need to know a little bit about electrical safety. If the current, that is the amount of electrons that are trying to squeeze through a wire every second, gets too high, it could cause the wire to overheat and start a fire. When that happens, we say that the circuit is overloaded. Circuit breakers are switches that open a circuit when the current gets too high, and they do this to prevent fires. If the current gets very high and the wire starts to get hot, the circuit breaker will open the switch, which opens the circuit and stops the flow of electrons and lets those wires cool down. One of the nice things about circuit breakers is that if they open, because you've overloaded a circuit, you can go reset them. Typically this is done at a circuit breaker box that you'll find in the basement of your house. Fuses have the same purpose. Their job is to open a circuit when the current flow gets too high. But fuses do this a little bit differently. Instead of being a switch that you open, a fuse is just a wire that's designed to actually melt and break when the current gets too high, and they need to be replaced. These you'll often find in your car, so that if for some reason you end up with too much electricity flowing through one circuit in your car, you'll blow a fuse and then there won't be a fire.